This should be a really quick video just going over some different notations or symbols or things you see in writing that are asking you to either find the derivative or telling you that something is the derivative. And so let's look at some of these notations. And in all of these, we're going to let y equal f of x be your original function. So for the first derivative, the notations that most people are familiar with going into the beginning of differentiation rules are the y prime and the f prime notations. However, there are some other notations that carry the same meaning. And these two right here, the dy dx and the ddx, or you can say dy over dx if you want. But these two notations right here are probably my favorite, even though they're a little bit uglier. But those are called Leibniz notation. Leibniz was just one of the, I think I spelled that right. Ooh, I hope so. The gods of math would be mad at me. But that's called Leibniz notation. And Leibniz was just another developer of calculus way back in Newton's time, when calculus was first getting underway. And he came up with that dy dx, ddx notation. And then another one, and this is an operator right here. We're not going to use that much at all. As a matter of fact, I feel fairly confident in saying that after this video, for my students, you're not going to see that anymore. Anybody else around the world watching this, who knows what you're going to see. But that's an operator, and I'll talk about what that means in a second. Operator notation. So let's talk about Leibniz notation and some of the reasons why I love Leibniz notation. And the main reason is because of what the derivative represents. The chief purpose of a derivative is to tell you the slope of the function at a point. And if you think about slope, the formula for slope that you learned in Algebra 1 was a change in y over a change in x. And if you look at Leibniz notation, he simply replaced the deltas with a d. And the reason he did that is because the delta y, delta x, you actually have to have 2 points that you can measure the distance between. In calculus, we're doing the slope at a single point on a curve. And if I'm finding the slope at a single point, you no longer can measure the distance. It's an immeasurable, infinitely small distance. And that's what that little d is representing. So I like Leibniz notation because it literally is a reference to change in y over change in x. It screams slope. And I'll talk about a few other things I like about it. So let's look at the difference in those two. So we have the dy dx and then we have ddx, and they do carry slightly different meanings. So the dy dx is really a noun. Dy dx is telling you that the derivative is this thing. So for example, if I have y equals x cubed minus 4x, I could write dy dx, the derivative is 3x squared minus 4. So that's what the dy dx means. However, the ddx is really an operator, kind of like this capital D with the subscript x, and that is commanding you to find the derivative. So if you see ddx, that's telling you to find the derivative of whatever follows. So an example of the correct usage of ddx would be this. ddx parentheses this is telling you to find the derivative of that function, and the derivative of that function is 3x squared minus 4. And that is also the same way that the capital D with the subscript x is used. So dx of x cubed minus 4x would equal the derivative with respect to x of this is 3x squared minus 4. So that is the Leibniz notation. That's how the operator notation works. And the difference between dy dx and ddx is explained right there. Something else I like about Leibniz notation, and this is a preview of something we're going to see later on in life. And this right here, this line right here is the first step in something that is called implicit differentiation that we will do later on in life. And what I like about Leibniz notation is that the dy dx, the representation of the derivative in this line, is very, very obvious. It's big, it's loud, it's obnoxious, it's in your face. It's like my mother-in-law. So I like it because you really can't avoid it, unlike my mother-in-law. But anyway, whereas if you use the y prime notation, there's absolutely nothing wrong with using y prime instead of dy dx. But the problem is y prime looks very similar to y. And if you write all of this and you just have y primes, you may lose that prime notation and you may accidentally mess up the algebra, whereas the dy dx is really hard to lose. So I prefer dy dx for that reason. and also the reason that it references the slope, change in y over change in x. But there is an overview of those derivative notations, and we should have already been familiar with y prime and f prime. So there are some notations for the first derivative. Now let's get into higher order derivatives. So like the second derivative, the third derivative, and so on and so forth, all the way down to however large you want to get. And if you look at the second derivative, you already knew the y double prime and the f double prime notation. That's fairly standard, and a lot of people like that because it's easiest to write. But look at the Leibniz notation and the placement of those exponents. This does mean the second derivative. That is not the first derivative squared. I can't think of a reason to square the first derivative. So this is the second derivative, and the exponents are in those locations for a very good reason. And the best reason I can explain that is easiest to understand is that for the second derivative, you are finding the derivative of the first derivative. So let's use notation, Leibniz notation, to put that sentence into math symbols. Find the derivative of the derivative. Well, the first derivative would be dy dx, and I am commanding you to find the derivative of that. So I'm now going to use the operator version of Leibniz with the noun of Leibniz. And if you look at that, we're finding d, the derivative of dy. So that's two d's and a y, which can be written as d squared y. And then in the denominator, I have two entire dx's. And so we write that as dx squared. Now, I know in algebra, you probably are thinking that the dx should be in parentheses, but we don't do that with Leibniz notation. We just leave it like this. So there is why the exponents are where they are. And it's the same thing with this operator notation with the subscript x. The exponent of 2 is really not an exponent. That's telling you the order of the derivative. So there is the notations for the second derivative. And once you see the second derivative, the third derivative is pretty predictable. Y triple prime, f triple prime, d cubed y over dx cubed, so on and so forth. So there's your third derivative. And then I want to skip down to a really higher order. I'm going to skip all the way to the 17th derivative. And for the Leibniz notation and the operator, it's pretty predictable. It's going to be the 17th derivative of y with respect to x, or the operator would be d17 over dx17. And then the operator notation of d subscript x would just be d with the subscript x and an exponent looking thing of 17. So those were predictable, and that's another good thing about the Leibniz notation is the notation is standard even through higher orders of the derivatives. However, if you were using the prime notation would get really cumbersome when you get to higher orders, like f 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 would be really stupid. That's too hard to count. Would be easier to count if you use tally marks, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and so on and so forth. But that also is stupid. So when you get to higher order derivatives with the prime notations, what we do is we put the order of the derivative in parentheses as an exponent. So it looks like an exponent, but the parentheses set it apart from the exponent, and it's actually telling you to find that order derivative. Same thing, f with an exponent of 17 in parentheses means find the 17th derivative of the function. Now note that that is not the same as exponents. So if you see, go to the thought bubble over here. If you see f5 of x, that is actually the function f of x raised to the fifth power. It is not the fifth derivative. F with a 5 in parentheses of x is the fifth derivative of f of x. So there are some derivative notations. So when you run into those, you'll know what they mean. And that is it. There we go.